The strangest fact about the universe is not its size. It is its beginning. Everything you have ever known, every star, every atom in your body, every grain of sand, every distant galaxy drifting through black space, all of it was once compressed into something so dense, so hot, and so small that the ordinary language of physics begins to fracture. Not billions of years ago, but within the first second. That first second is not just the beginning of the universe as we see it. It is the moment when the rules that allow anything to exist, space, time, matter, energy, structure, began arranging themselves into the form we now call reality. And the unsettling part is this. For most of that first second, the universe was not a place where anything familiar could survive. Not atoms, not light travelling freely, not even the stable forces that now hold matter together. For a brief and violent stretch of time, the universe existed in conditions so extreme that the difference between space and energy, between particle and field, may not have meant anything yet. The story of the cosmos begins there, inside a moment so small that if the entire 13.8 billion year history of the universe was stretched across one calendar year, the first second would pass before midnight on January 1st had finished its first breath. Yet nearly everything that followed was decided inside it. The shape of galaxies, the existence of stars, the chemistry that eventually formed planets, even the delicate balance that allowed matter itself to survive. To understand why, we have to step into a universe that did not yet resemble a universe at all. Picture the night sky for a moment. Thousands of faint stars. The pale river of the Milky Way cutting across darkness. Every one of those lights belongs to a galaxy made of hundreds of billions of stars, each surrounded by planets, gas clouds, and dark matter drifting through vast halos. Our telescopes now see billions of these galaxies, each one separated from the next by distances so enormous that light, the fastest thing in the universe, can spend millions or billions of years crossing the gaps between them. This enormous cosmic architecture feels ancient and stable, but all of it traces backward to a moment when none of those structures existed. No galaxies, no stars, no atoms, no empty space between objects. Because there were no objects yet. There was only a universe filled with energy so intense that matter could not hold its shape. If you could stand inside that early universe, and nothing resembling a body could, the temperature would have been so extreme that atomic nuclei could not survive longer than a fraction of a second. Electrons could not attach to them. Atoms could not form. Even the protons and neutrons inside atomic nuclei were still struggling to exist. Temperature is a word we use casually. A warm afternoon, a hot engine, the surface of the sun. But in the first moments after the Big Bang, temperature meant something closer to violence. At around 1 trillion degrees Celsius, particles collide with such energy that matter continuously breaks itself apart. Imagine every atom in your body moving so violently that it cannot stay assembled. Now increase that violence by another factor of 1 billion. That is closer to the early universe. And yet even this description is already too calm. Because in the earliest fraction of the first second, the temperature was not merely trillions of degrees. It was likely above 10 quadrillion degrees. A number so large it stops behaving like a temperature and begins behaving like pure energy. Under those conditions, the known forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may not have existed as separate things. Today those forces govern everything. Gravity shapes galaxies. Electromagnetism holds atoms together and carries light across space. The strong force binds protons and neutrons inside nuclei. The weak force governs radioactive decay and the nuclear reactions inside stars. But in the earliest instant of the universe, these forces may have been unified. Different expressions of a single underlying interaction. A kind of primordial symmetry. A universe so hot that the distinctions between the rules had not yet emerged. Then the universe began to expand, not like an explosion throwing matter outward through space, but like space itself stretching, every distance growing, every region moving away from every other region. As space expanded, energy spread out, temperature fell, and something subtle but profound began to happen. The universe started cooling enough for differences to appear, like a liquid slowly freezing into crystals. The unified force may have begun separating into the individual forces we observe today. Gravity possibly split away first, then the strong force, then electromagnetism and the weak force, still briefly connected before they too separated. These transitions were not gentle. They were cosmic phase changes, comparable in principle to water turning into ice, but happening at energies so extreme that the consequences shaped the entire structure of the universe, and all of it unfolding in fractions of a second. To grasp how quickly this happened, it helps to compress time until it becomes almost uncomfortable to imagine. 1,000th of a second, a millisecond. That is roughly the time it takes a camera flash to fire. Inside that time, your brain barely registers the event. But the earliest moments of the universe unfold on scales far smaller. A microsecond is 1/1,000,000th of a second. A nanosecond is 1/1000,000th. But even these are enormous compared to the earliest moments after the Big Bang. Physicists often talk about the Planck time, about 5 times 10 to the minus 44 seconds, a number so small that if you counted Planck times from the beginning of the universe until now, you would reach a figure with more digits than there are atoms in many galaxies. Below that scale, our current physics stops making reliable predictions. Space and time themselves may become turbulent. Quantum fluctuations in the geometry of spacetime could dominate. The smooth universe we describe with general relativity dissolves into something more uncertain, something more granular, something we do not yet fully understand. So the story of the universe does not begin with perfect clarity. It begins with a boundary, a point where our theories can look backward only so far before the equations stop behaving. But just beyond that boundary, a tiny fraction of a second later, the universe had already begun its transformation. Energy filling every direction, space expanding, temperature dropping fast enough for the first recognizable ingredients of matter to appear, and those ingredients would eventually become everything. Your bones, the air in your lungs, the iron in your blood, the calcium in your teeth, the oxygen produced inside ancient stars. All of it traces backward through billions of years of cosmic history, through collapsing clouds of gas, through nuclear reactions inside stellar cores, through supernova explosions that scattered heavy elements across galaxies, and further still, past the birth of the first stars, past the formation of atoms, past the time when the universe was a blinding sea of radiation, until the trail ends in that first second, a moment when the universe was not yet a landscape of galaxies, but a furnace of energy, a place where the seeds of everything were being written into the structure of space itself. And the unsettling truth is that the universe we inhabit today, calm, structured, filled with stars and planets and quiet night skies, is not the natural state of reality. It is the cooled aftermath, the quiet residue of an opening moment so extreme that it reshaped the laws of nature themselves, a distant echo of a time when the universe was not yet stable enough to hold a single atom. And the deeper we look into that first second, the more we realize something strange. The universe did not simply begin and then slowly evolve. It changed character repeatedly, rapidly, violently. Different eras stacked almost on top of each other, each lasting less time than the blink of an eye, each rewriting what the universe was allowed to become. By the time that first second finally ended, the stage for the entire cosmic story had already been set. Matter existed, forces had separated, the universe was expanding and cooling, and the first fragile pieces of the world we know had begun to assemble. But the most astonishing part of the story had already happened earlier, long before atoms, long before particles, even before the first trillionth of a second had finished passing. Because somewhere inside the earliest sliver of time, the universe underwent a transformation so sudden and so enormous that it stretched space itself faster than light could travel. A brief event that took a microscopic universe and blew it outward into the vast cosmic arena we inhabit today. The first second had barely begun, and already the universe had changed forever. Time had barely begun. Not metaphorically, literally. There was a moment, unimaginably early, when the universe had existed for less than a trillionth of a second. A span so small that if a human blink lasted 1 second, the early universe passed through entire eras before that blink even started. Inside that vanishing fraction of time, The universe was not quiet, not empty, and certainly not simple. It was a furnace of energy so intense that the distinction between matter and radiation barely held. Particles flickered into existence and vanished again. Space itself was swelling outward. And time, the slow, reliable flow we live inside, was only just beginning to behave like time. The strange part is that the universe did not begin large and then slowly cool. It began unbelievably hot and dense, and every fraction of a second afterward was a release of pressure, a cosmic exhale. Imagine compressing every galaxy we can observe, all the clusters, the dark matter halos, the voids stretching across hundreds of millions of light years, squeezing them inward until the entire observable universe becomes smaller than a grain of sand. Not metaphorically, physically. That is roughly the density implied by the earliest moments we can meaningfully describe. But the problem with imagining that scene is that it suggests something sitting inside a larger space. The early universe had no outside. There was no surrounding darkness waiting beyond its edges. Space itself was the thing expanding, every point moving away from every other point, not because something pushed them outward, but because the geometry of space was stretching. The same strange effect still happens today. Galaxies drift away from one another as the universe expands. But in the earliest moments, that expansion was far more violent. Temperature and density were falling with astonishing speed. And as they fell, the universe began to cross invisible thresholds, critical temperatures where the rules of physics reorganized themselves. These thresholds behave a little like freezing points. When water cools below 0 degrees Celsius, something sudden happens. The molecules stop sliding freely. Crystals form. The liquid becomes solid. The early universe passed through similar transitions, except instead of ice forming, the fundamental forces themselves were separating from one another. At extremely high energies, many physicists suspect that the electromagnetic force and the weak nuclear force were once the same thing, a unified interaction. In laboratories today, we can actually glimpse this connection. Inside particle accelerators, when protons collide at enormous energies, the distinction between those two forces begins to blur. At around 100 billion electron volts, energies achievable in modern colliders, they merge into what physicists call the electroweak force. But the early universe went far beyond that. Temperatures were trillions of times higher than anything humanity has ever produced. At those energies, the electroweak force behaved as a single unified field. Particles that now behave very differently were once almost indistinguishable. Electrons, neutrinos, quarks, the ingredients of matter, were immersed in a blazing ocean of radiation. Nothing could sit still. Nothing could cool. Every particle was constantly colliding with others at speeds approaching light. If you could somehow place a thermometer into that environment, an impossible instrument, it would read around 10 trillion degrees. At that temperature, protons and neutrons cannot exist yet. Quarks, the particles that normally live trapped inside them, roam freely. Instead of atomic nuclei, the universe was filled with what physicists call a quark-gluon plasma, a state of matter so energetic that the strong nuclear force, the interaction that normally binds quarks together, could not keep them confined. Imagine trying to build a snowball in the middle of a volcanic eruption. Every time you pack snow together, the heat melts it instantly. That was the situation for matter. Particles formed briefly, then shattered apart again, and yet this chaos was not random. Hidden within the turbulence were delicate statistical imprints, tiny variations in density and energy scattered across space. They were incredibly small. In some regions, the universe might have been just 1 part in 100,000 denser than the surrounding space. That sounds trivial, but gravity is patient. Given enough time, even a tiny imbalance becomes destiny. Those faint irregularities would later grow into galaxies, into clusters, into the large-scale cosmic web stretching across billions of light years. The night sky you see today began as microscopic ripples in that early furnace, but the universe was still far too hot for those ripples to matter yet. Gravity could not gather material while radiation dominated everything. Light itself was constantly scattering off charged particles. Photons could barely travel a fraction of a millimeter before smashing into electrons and quarks. The entire cosmos was opaque. Not dark, blindingly bright. If sight were possible, Every direction would glow with uniform, searing light, a horizonless ocean of radiation. And yet this brightness carried a strange secret. The light filling that early universe still exists today, stretched, cooled, diluted by billions of years of expansion. Every cubic centimetre of space around you right now still contains about 400 of those ancient photons. They have cooled to just 2.7 degrees above absolute zero. Microwaves instead of visible light. But they are survivors from that early time. Relics of a universe that once burned at temperatures hotter than the core of any star that would ever exist. The discovery of this radiation in 1965 was one of the great confirmations of the Big Bang. Two radio engineers, Arno Penzias and Robert Wilson, were testing a large antenna in New Jersey. No matter where they pointed the instrument, they detected a faint hiss of microwave noise. Day or night, summer or winter, they cleaned bird droppings from the antenna. They checked their equipment again and again, but the signal remained. What they had found was not interference. It was the afterglow of the early universe itself, a whisper from nearly 14 billion years ago. But when that radiation first filled the universe, it was not faint. It was the dominant force shaping everything. And during the first fractions of a second, something remarkable began happening to the particles swimming inside it. As the temperature dropped below certain thresholds, quarks could finally begin binding together. 3 quarks joined to form protons and neutrons. These particles were still rare and unstable in the earliest moments, but gradually the violent collisions became just gentle enough for them to survive. The strong nuclear force, once overwhelmed by heat, finally gained control. Matter began to take recognizable form. If you could pause the universe around 1/1,000,000th of a second after the beginning, the environment would still be unimaginably hostile. The temperature would be around 10 trillion degrees. The density would exceed anything found inside modern stars. Yet for the first time, protons and neutrons would exist as stable particles. The raw ingredients of atomic nuclei had arrived. That may sound like a small step, but it was enormous. Everything familiar, every atom in your body, depends on those particles existing. Without them, chemistry cannot exist. Stars cannot form. Planets cannot assemble. Life cannot emerge. The universe had crossed its first major threshold. Energy was becoming matter, but the story was not yet stable, because something else was happening in the background. Something subtle. Something that would determine whether matter survived at all. For every particle produced in those early moments, physics predicts a partner should also appear. Antimatter, a mirror version of matter with opposite electric charge. When matter meets antimatter, they annihilate. Pure energy, no leftovers. In the violent particle storms of the early universe, matter and antimatter were created constantly. Electrons and positrons, quarks and antiquarks, particle pairs appearing and vanishing like sparks. If the universe had produced exactly equal amounts of both, they would eventually have destroyed each other completely. The cosmos would have cooled into a sea of radiation with no atoms. No stars, no galaxies, no observers. But that did not happen. Somewhere in the earliest moments, a tiny imbalance appeared. For roughly every billion antimatter particles, there were 1,000,000,001 matter particles. Just one extra. It sounds insignificant. But when annihilation swept through the early universe, those lonely survivors remained. Every proton, every neutron, every atom you know, all of them descended from that tiny statistical advantage, a slight asymmetry written into the physics of the first second. The universe we inhabit exists because matter won that microscopic war, but the origin of that imbalance remains one of the deepest unsolved questions in physics. Something in those early moments tipped the scales. Something subtle. Something still hiding in the laws of nature. And it happened long before the first second of cosmic time had even finished passing. Because the early universe was not simply cooling and forming particles. It had already experienced an event far stranger. A brief era when space itself expanded faster than light could travel. A moment so sudden that it took a universe smaller than an atom, and stretched it to astronomical size. An event that would quietly determine the shape of everything that followed. And it happened almost immediately after time itself began to flow. By the time the universe was 1/1,000,000th of a second old, something remarkable had already happened. The rules of nature had begun separating, not gradually, abruptly. The universe had cooled just enough for the smooth symmetry of the earliest moments to fracture into distinct forces, each governing a different piece of reality. Today those forces feel permanent. Gravity bends space and gathers galaxies. Electromagnetism holds atoms together and carries light across the universe. The strong nuclear force glues quarks into protons and neutrons. The weak force quietly governs radioactive decay and the reactions that power stars. They seem like separate laws, independent, unrelated, but the early universe hints that they were once the same thing. At extremely high energies, differences between forces begin to fade. Physicists see this even in modern experiments. Inside particle accelerators like CERN's Large Hadron Collider, when particles collide with enough energy, the electromagnetic force and the weak force merge into a single interaction. The electroweak force. At lower energies, the energies of ordinary life, those forces behave differently. But raise the temperature high enough and the distinction dissolves. Now imagine temperatures trillions of times higher than those experiments. The early universe reached them easily. Under those conditions, the forces we know may have been part of a deeper unity, a single framework governing every interaction. Then the universe cooled, and the symmetry cracked. Think of cooling metal. At high temperature, atoms inside the metal move chaotically. The structure is uniform, but as it cools, the atoms settle into organized patterns. Crystal structures form. The material acquires properties it did not have before. The early universe experienced similar transitions, except instead of crystals forming, the laws of physics themselves were reorganizing. One by one, forces separated. Gravity may have peeled away first, becoming the gentle but relentless curvature of space-time that shapes the motion of planets and galaxies. Then the strong nuclear force split from the electroweak interaction, gaining the strength necessary to bind quarks together. Later still, the weak force and electromagnetism separated, leaving the familiar interactions that shape atoms and chemistry today. Each separation was a phase transition. Not quiet, not slow. These were moments when the structure of reality shifted. Fields rearranged themselves. Energy landscapes changed, and the universe entered new states of behavior. But there is a deeper strangeness hidden here. When physicists talk about forces separating, they are not imagining objects pulling apart. They are describing something happening inside fields. Modern physics sees the universe not as empty space filled with particles, but as a network of fields extending everywhere. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Quarks are ripples in their own quantum fields. Even empty space is not truly empty. Fields exist everywhere. Particles appear as excitations moving through them. In the earliest moments of the universe, these fields behaved differently. The Higgs field, the field responsible for giving many particles their mass, likely had a different configuration. At extremely high temperatures, it may have had zero value everywhere, which means particles moving through it had no mass. Massless particles behave differently. They cannot sit still. They must travel at the speed of light. So in those earliest instants, many particles that are heavy today would have behaved as if they were weightless. A strange, ultra-fast universe. A place where the ingredients of matter existed, but their familiar properties had not yet settled into place. Then the temperature dropped. The Higgs field changed state. Like water freezing, suddenly particles acquired mass. The behavior of matter shifted dramatically, and the universe entered a new phase of physical law. These changes were not visible explosions. No sparks, no shock waves in the ordinary sense, but the consequences were immense, because every phase transition can leave behind imperfections. When ice forms, cracks appear. When crystals grow, defects form inside the structure. In the early universe, similar defects might have emerged inside the fabric of space itself. Physicists call them topological defects, cosmic strings, domain walls. Structures formed when different regions of space settled into slightly different configurations of fields. If they exist, these objects could stretch across enormous distances, thinner than atoms, yet incredibly dense. Some theories suggest that a kilometre of cosmic string could weigh more than a mountain. So far none have been conclusively observed, but the possibility remains. relic scars from the universe's earliest phase transitions. Even without such exotic remnants, something else survived from that era. Tiny fluctuations, small variations in energy and density. Not random noise, quantum fluctuations, the kind of uncertainty that exists even in empty space. At the smallest scales, quantum physics tells us that fields cannot remain perfectly still. They jitter. Energy briefly appears and disappears. Particles flicker into existence and vanish again. These fluctuations normally remain microscopic, invisible, but in the early universe something extraordinary happened. Space was expanding, rapidly, and those tiny fluctuations were being stretched. What began as quantum jitter at subatomic scales was pulled outward into macroscopic ripples in density, ripples that would later guide the formation of galaxies. The universe was taking microscopic randomness and imprinting it onto cosmic structure. But at this stage, the universe was still too young for gravity to shape those fluctuations. Radiation dominated everything. Energy filled every direction. Particles collided constantly. Light scattered in every direction. If you could stand there, impossible though it would be, the brightness would be absolute. No shadows, no darkness, just a uniform ocean of blazing radiation. The density would be crushing. In the first microsecond, the universe contained roughly the mass of the entire observable cosmos packed into a region far smaller than a star. Matter and energy were almost interchangeable. Every collision energetic enough to create new particles. The universe was a particle factory. Quarks, antiquarks, electrons, neutrinos, gluons carrying the strong force, photons carrying light, a turbulent plasma of fundamental ingredients. Yet even inside this chaos, something important was stabilizing. Protons and neutrons, the building blocks of atomic nuclei, had begun forming and surviving. The strong force had finally gained control. Quarks were no longer free. They were confined inside composite particles. Matter was becoming durable. The temperature at this stage was around 10 trillion degrees. Still unimaginably hot. Hot enough that atomic nuclei could not yet form stable combinations. But cool enough for the first recognizable particles of matter to persist. The universe was only about 1/1,000,000th of a second old. And yet the basic components of every future atom had already appeared. If time could pause there, the cosmos would look like an intensely bright fog of particles. No stars, no atoms, just a dense plasma where protons, neutrons, electrons, neutrinos, and photons collided endlessly. Light could not travel far. Every photon scattered off charged particles almost immediately. The universe was opaque. Radiation dominated. Gravity was still waiting. But beneath the brightness, something subtle was building. Because those tiny fluctuations, the stretched quantum ripples, had not disappeared. They were still present. Barely measurable differences in density across space. Some regions slightly denser, others slightly emptier. They were small, about 1 part in 100,000. Yet those tiny differences would eventually decide where galaxies formed, where clusters gathered, where cosmic voids opened between vast structures. The early universe was laying down the blueprint of everything, quietly, statistically, inside a furnace of unimaginable heat, and all of it was happening before the universe had even reached its first second. But the most dramatic transformation was still coming, a moment so violent that it would stretch the universe faster than light could travel. A brief era when space itself expanded at a pace so extreme that entire regions of the cosmos were torn apart faster than information could cross them. A moment when the universe grew from microscopic to astronomical, almost instantly. The event physicists now call inflation, and without it, the universe we see today would look nothing like the one we inhabit. There was a moment, very early in cosmic history, when the universe did something that still feels almost impossible to say out loud. It expanded faster than light. Not matter racing through space faster than light. That would break the rules of relativity. Instead, space itself stretched. Distances grew so quickly that 2 points in the universe could move apart faster than a beam of light could cross the gap between them. And for a brief instant, that expansion was not just fast. It was explosive. This event is called inflation. It may have lasted less than a trillionth of a trillionth of a trillionth of a second. Yet in that tiny sliver of time, the universe expanded by a factor so enormous that a region smaller than an atom may have ballooned to the size of a galaxy. To understand how strange that is, imagine drawing a dot on a rubber sheet. Now stretch the sheet. The dot does not move across the surface, but every distance around it grows. Points separate because the surface itself expands. Cosmic inflation worked in a similar way. Space itself was stretching. Everywhere. All at once. Before inflation began, the universe may have been unimaginably small, possibly smaller than a proton. Dense beyond comprehension. Energy packed so tightly that the familiar structure of fields and particles barely had time to settle. Then something changed in the energy of the vacuum. That phrase sounds abstract. But the vacuum in physics is not empty nothingness. It has structure. Fields fill every part of space, even when no particles are present. Those fields contain energy. Normally that energy is stable, but in the earliest universe, the vacuum may have briefly occupied a higher energy state, something like a ball resting on a flat plateau rather than inside a valley. In that configuration, the energy density of space itself remained almost constant even as the universe expanded. And that constant energy density had a strange effect. It produced a kind of repulsive gravity. Instead of pulling space inward, it drove space outward. Expansion accelerated. Not gradually, exponentially. Every fraction of a moment distances doubled. Then doubled again. And again. In a time interval so small it defies intuition, the universe may have expanded by a factor of at least 10 to the power of 26. That is 100 million trillion trillion. If a proton experienced that same growth, it would become larger than the visible universe. The expansion was so violent that any curvature in space was flattened. Before inflation, the geometry of the universe could have been chaotic, bent in complicated ways. After inflation, those curves were stretched smooth, like wrinkles pulled tight across an enormous surface. This explains something that once puzzled cosmologists. When we look across the sky in opposite directions, regions of the universe separated by tens of billions of light years have nearly identical temperatures. The cosmic microwave background, the faint radiation left from the early universe, is almost perfectly uniform. But without inflation, those regions would never have had time to exchange information. Light could not have travelled between them. They should look different. Yet they do not. Inflation solves this mystery. Before the rapid expansion, those distant regions were once close together, close enough to reach the same temperature, close enough to share physical conditions. Then inflation stretched them apart faster than signals could travel. Regions that were once neighbours became separated by unimaginable distances. The uniformity we observe today is a fossil of that earlier closeness. But inflation did more than smooth the universe. It also magnified the tiniest imperfections. Remember the quantum fluctuations from the earliest moments, the microscopic jitter inside fields. Normally, those fluctuations remain confined to extremely small scales. But during inflation, space expanded so quickly that these tiny ripples were stretched outward. What began as subatomic variations became astronomical differences in density. It was as if the universe took microscopic noise and turned it into a cosmic blueprint. Those stretched fluctuations became the seeds of structure. Regions slightly denser than average would later attract matter through gravity. Gas would gather. Stars would ignite. Galaxies would assemble. Clusters of galaxies would grow along filaments stretching across space. Every galaxy we see today may trace its origin back to quantum fluctuations smaller than a proton. A strange idea. The large-scale architecture of the cosmos emerging from quantum uncertainty. Inflation ended as suddenly as it began. At some point, the vacuum field driving expansion fell into a lower energy state. The plateau vanished. The ball rolled into the valley. The repulsive gravity switched off. Space stopped expanding exponentially. But the energy stored in that field did not disappear quietly. It decayed into particles, a flood of radiation and matter. Physicists call this process reheating. The universe filled again with particles and light. Temperature soared. The cosmic furnace reignited. In some sense, the hot Big Bang, the dense plasma of particles we discussed earlier, may actually be the aftermath of inflation ending. The universe was reheated. Energy poured into particle fields. Quarks, gluons, electrons, neutrinos, and photons filled space again. The cosmic story resumed. But now the stage had changed. Space was vastly larger, almost perfectly smooth, yet carrying faint imprints of those stretched quantum fluctuations. Those faint variations, about 1 part in 100,000, would later appear as tiny temperature differences in the cosmic microwave background. We have measured them. Satellites like COBE, WMAP, and Planck mapped these fluctuations across the sky with astonishing precision. What they revealed looks almost like static on an old television screen. Tiny speckles of slightly warmer and slightly cooler radiation. But those speckles are not noise. They are fossils, frozen fingerprints of the earlier structure in the universe. Evidence that the seeds of galaxies existed when the universe was less than a second old. Possibly much earlier. Inflation explains several puzzles at once. Why the universe is so uniform. Why its geometry appears nearly flat. Why large structures grew from tiny initial fluctuations. Yet despite its success, inflation remains partly mysterious. We do not yet know which field caused it. We do not know exactly how it began, or how many times it may have occurred. Some theories suggest inflation might happen repeatedly in different regions of space, creating multiple expanding universes, a vast multiverse. Other theories suggest inflation might arise from deeper physics we have not yet discovered. For now, the evidence comes indirectly, from patterns in the cosmic microwave background, from the large-scale distribution of galaxies, from the statistical imprint left by those ancient fluctuations. Every measurement so far fits remarkably well with the predictions of inflation, which means the universe we inhabit, the galaxies, the stars, the quiet night sky, may ultimately owe its structure to a brief, violent expansion that lasted far less than a second. An expansion so extreme that it turned quantum tremors into cosmic architecture. But when inflation ended, the universe did not suddenly become calm. It was still unimaginably hot, still filled with energy, still evolving at a furious pace. Particles were forming, annihilating, colliding. The cosmic furnace was entering a new phase, because now, as the universe continued to cool, the ingredients of matter would begin assembling into more stable forms. Quarks binding permanently into protons and neutrons, the first building blocks of atoms, the raw material of every star that would ever burn. And this transformation would unfold inside a universe still less than a second old. A universe racing forward through its earliest moments, still carrying the violent memory of inflation, still expanding, still cooling, still writing the physical rules that would shape everything that followed. When inflation ended, the universe did not settle into calm. It erupted. The energy that had been driving the expansion did not simply fade away. It poured back into the universe, converting into an immense flood of particles and radiation. Physicists call this reheating, though the word sounds almost gentle compared to what actually happened. Space, which had just undergone a staggering burst of expansion, suddenly filled with an ocean of energy dense enough to ignite the cosmic furnace again. The temperature soared, not to the unimaginable extremes of the earliest instance, but still to levels far beyond anything that would ever exist inside stars. Particles began to appear everywhere. Quarks, antiquarks, electrons, neutrinos, gluons carrying the strong force, photons carrying light. Everywhere you looked, if looking were possible, particles were colliding with extraordinary violence. The universe had become a particle storm. Yet something fundamental had changed compared to the time before inflation. Space was now vast. Not infinite in the ordinary sense, but enormously expanded compared to the microscopic beginning. And within that expanding space were faint imprints left behind by the inflationary stretch. Those imprints were subtle, barely measurable differences in energy density scattered across space. In some regions, the energy of the universe was slightly higher, in others slightly lower. The differences were tiny, about 1 part in 100,000. If the universe were the height of Mount Everest, the fluctuations would be less than a centimetre. Almost invisible, but gravity is sensitive. Even the smallest imbalance becomes important when time stretches across billions of years. The early universe was laying down its blueprint. Quietly, Statistically, those slight variations in density would eventually decide where matter accumulated, where gas clouds collapsed, where stars ignited, and where galaxies would take shape. But for now, gravity was not yet the dominant actor. Radiation ruled the universe. Photons outnumbered matter particles by enormous margins. The entire cosmos was filled with light constantly scattering off charged particles. Imagine fog so thick that a flashlight beam cannot travel more than a few millimeters before bouncing off droplets. Now replace the droplets with electrons and protons. Replace the flashlight with photons carrying immense energy. That was the early universe. Opaque. Blinding. Every photon ricocheting endlessly from particle to particle. Light could not travel freely. The universe was filled with brightness, but there was no clear sky. Inside this searing plasma, the particles that would one day form atoms were still struggling to exist. Temperatures were around 10 trillion degrees Celsius. At those energies, protons and neutrons were only just becoming stable. Before this moment, quarks had moved freely through space, unconfined. But as the universe cooled past a critical temperature, roughly 2 trillion degrees, something remarkable happened. The strong nuclear force took hold. Quarks became trapped together. 3 quarks bound into protons and neutrons, the same particles that form the nuclei of atoms today. Physicists call this event confinement. It was one of the earliest decisive transitions in cosmic history. Before confinement, matter existed as a quark-gluon plasma, a chaotic soup of free quarks and gluons. After confinement, quarks were locked permanently inside composite particles. The basic architecture of matter had appeared, and it happened when the universe was only about a millionth of a second old. That moment may seem almost absurdly early, but the shift was enormous. Protons and neutrons are stable enough to survive the violent particle collisions of the early universe. Without them, nothing resembling ordinary matter could ever form. Yet even now the universe remained hostile to the formation of anything larger. Atomic nuclei could not yet survive. Temperatures were still far too high. If 2 protons collided and briefly formed a nucleus, the surrounding radiation would blast it apart almost immediately. Matter was stable only in its simplest forms. But beneath the chaos, something else was unfolding quietly. Neutrinos were beginning to slip away. Neutrinos are strange particles. They interact with matter only through the weak nuclear force. That means they pass through most material almost without noticing it. Billions of neutrinos are passing through your body every second right now, streaming from the sun and from distant cosmic events. You feel nothing. You see nothing. They barely interact. In the early universe, neutrinos were initially trapped inside the dense plasma of particles. They collided frequently enough to remain in equilibrium with the rest of the cosmic soup. But as the universe expanded and cooled, collisions became less common. The density dropped. The mean distance between interactions grew larger. Eventually, neutrinos stopped interacting often enough to stay coupled to the rest of the plasma. They decoupled. At that moment, they began traveling freely through space, a ghostly background of neutrinos filling the cosmos. This happened when the universe was about 1 second old. A single second. That is all it took for the universe to reach a stage where entire classes of particles could begin moving independently through space. Today, that ancient sea of neutrinos still exists. Trillions of them pass through every square meter of your body each second. Relics from the earliest moments, almost impossible to detect, but part of the same cosmic background that fills the universe with ancient light. The universe was still incredibly hot, around 10 billion degrees. Protons and neutrons moved through a dense fog of electrons and photons. Yet the environment was changing quickly. Temperature was falling. Expansion was relentless. And soon another critical threshold would arrive. At about 1 billion degrees Celsius, protons and neutrons could begin assembling into something new. Atomic nuclei. Not full atoms yet. Electrons still move too violently to attach themselves. But the cores of atoms, hydrogen nuclei, helium nuclei, the earliest forms of chemical structure. This moment, only a few minutes after the beginning, would quietly determine the elemental composition of the universe. How much hydrogen? How much helium? How much lithium? Those proportions would remain largely unchanged for billions of years. They would shape the formation of the first stars, the chemistry of galaxies, the evolution of planets, even the long chain of events that eventually led to life. All of that chemical destiny began unfolding in a universe still younger than a cup of coffee left cooling on a table. The early universe moved fast. Phase transitions, particle formation, neutrino decoupling, the assembly of nuclei, all of it stacked within moments. Yet underneath those dramatic transformations, the faint ripples left by inflation remained quietly embedded in the structure of space. Those fluctuations were still tiny, still almost invisible, but gravity had begun to notice them. In slightly denser regions, matter and radiation lingered just a little longer. Energy flowed slightly differently. These were the earliest hints of structure, the faintest beginnings of cosmic architecture, the seeds from which galaxies would eventually grow. The early universe was not just cooling, it was organizing. Tiny imbalances, magnified by time, were shaping the destiny of matter. But there was another fragile condition hidden inside this process, one that almost erased everything. Because while matter had begun assembling into protons and neutrons, antimatter had been forming as well, and the universe was approaching the moment when the two would collide on a cosmic scale. Particle by particle. Matter meeting antimatter, annihilating into pure energy. A war between mirror images, and when it ended, almost everything would vanish. Almost. For a long time, the universe was nothing but light, not the soft glow of starlight or the scattered shimmer of galaxies across the night sky. Something far more absolute, every direction filled with radiation so intense that the idea of darkness had not yet become meaningful. The universe was still less than a second old. Temperature hovered around 10 billion degrees. Matter existed, but only barely. Protons and neutrons moved through a blazing sea of photons, electrons, and neutrinos. Every particle collided constantly. Every motion was interrupted. Nothing could travel very far without striking something else. If you could somehow place a single photon into that environment and watch its journey, it would not travel freely across space the way light moves today. Instead, it would ricochet, bounce off an electron, scatter into another direction, strike another charged particle, change course again, over and over. The average distance between these collisions was incredibly small. A photon might travel less than the width of a human hair before being deflected again. The universe was not transparent. It was opaque, not because it was dark, but because it was too bright. Light was everywhere, but it could not escape. It was trapped in an endless dance of collisions. This state of matter is called plasma, a hot ionized gas where electrons are stripped away from atomic nuclei, leaving charged particles free to roam. In plasma, electromagnetic forces dominate. Charged particles constantly tug on one another through invisible fields. Stars are made of plasma. Lightning is plasma. The glowing interior of neon signs is plasma. But the early universe was plasma on a scale beyond anything familiar. The entire cosmos was a single, enormous plasma ocean. No atoms, no molecules, just charged particles and radiation in constant interaction. Yet even inside that blazing environment, the universe was slowly changing. Expansion was relentless. Every moment stretched space a little farther, and with every stretch, the energy density dropped. Temperature fell, not gradually on human timescales, but rapidly on cosmic ones. The universe was cooling at an astonishing pace. 1 second after the beginning, the temperature had already dropped to around 10 billion degrees, still far hotter than the core of the sun, but vastly cooler than the unimaginable heat of earlier moments. At this stage, something subtle happened. Neutrinos, those ghost-like particles that barely interact with matter, slipped away from the plasma. Earlier, the universe had been dense enough that neutrinos collided frequently with electrons and other particles. They remained part of the thermal soup, but as expansion diluted the cosmic plasma, collisions became rarer. Eventually, neutrinos stopped interacting often enough to stay in equilibrium. They decoupled. From that moment forward, they streamed freely through space. The universe became filled with a faint background of relic neutrinos, a silent wind of particles racing through the cosmos almost completely unnoticed. Even now, trillions of them pass through every square centimetre of your body each second. You feel nothing. They barely touch the atoms inside you. Yet they are ancient travelers, messengers from the universe when it was only 1 second old. The early cosmos was shedding layers of interaction. Particles that once moved together were beginning to separate into independent populations. But for most of the universe's contents, freedom was still impossible. Photons remained trapped. Electrons and protons were locked inside the dense plasma. Matter and radiation behaved almost like a single fluid. If you could somehow drift through that environment, immune to its heat and pressure, it would feel less like empty space and more like being submerged in a bright, invisible ocean. Every movement resisted by collisions, every direction filled with blinding energy. But beneath the brightness, another quiet transformation was underway. Protons and neutrons had already formed, yet they did not exist in equal numbers. Neutrons are slightly heavier than protons. Because of that extra mass, neutrons are less stable. Even today, a free neutron outside an atomic nucleus survives only about 15 minutes before decaying into a proton, an electron, and a neutrino. In the early universe, neutrons were constantly colliding with other particles. Those collisions kept protons and neutrons converting back and forth through the weak nuclear force. But as the universe cooled and expanded, those interactions slowed. Eventually, the rate of conversion could no longer keep up with expansion. The ratio of protons to neutrons froze. Roughly 6 protons for every neutron. That ratio would turn out to be crucial, because only minutes later, protons and neutrons would begin combining into the first atomic nuclei, and the number of neutrons available would determine how much helium could form. Helium nuclei require 2 protons and 2 neutrons. Without enough neutrons, helium would be rare. But because the early universe preserved that 1:6 ratio, helium would become the second most common element in the cosmos. The ingredients of chemistry were quietly being set, not by life, not by stars, but by the cooling physics of a young universe still younger than a minute. Yet the plasma remained fierce. Temperature hovered near 10 billion degrees. At these energies, any attempt to assemble a stable atomic nucleus was quickly undone. Photons were too energetic. They smashed fragile nuclear bonds apart. It was like trying to build a sandcastle in the middle of a hurricane. Every attempt collapsed almost immediately. The universe needed to cool further, and so it did. Seconds passed, then tens of seconds. Expansion continued. Temperature fell. At around 1 billion degrees Celsius, the environment finally became calm enough for nuclei to begin surviving. Protons and neutrons collided and occasionally stuck together. Deuterium formed, a hydrogen nucleus containing 1 proton and 1 neutron. Then helium. Then traces of lithium. This brief era of nuclear formation lasted only a few minutes. Yet during that short window, the universe produced nearly all the helium that still exists today. About 25% of the universe's ordinary matter by mass became helium nuclei during those first few minutes. The rest remained mostly hydrogen. Those proportions have barely changed since. Stars would later manufacture heavier elements, carbon, oxygen, iron, inside their nuclear furnaces. But hydrogen and helium were already present, born in the fading heat of the Big Bang, when the universe was still only minutes old, still glowing, still filled with radiation. Yet something about that early plasma still seemed strange, because even though matter had begun assembling into nuclei, the universe remained completely opaque. Light could not travel freely. Photons were still trapped in the plasma, bouncing endlessly from particle to particle. The universe remained a glowing fog, and it would remain that way for hundreds of thousands of years. Not seconds, not minutes, hundreds of thousands of years. The cosmos would continue expanding and cooling, waiting for a final threshold to arrive. A moment when electrons would finally slow down enough to attach themselves to atomic nuclei. A moment when atoms could exist. And when that happened, the plasma would vanish. Light would finally escape. The universe would become transparent for the first time. The afterglow of that moment still surrounds us today. A faint radiation field filling all of space. A whisper from a time when the universe was only 380,000 years old. But the story of that glow begins much earlier. Back here, inside the first seconds and minutes of cosmic time, when the universe was still a furnace of light, and the basic ingredients of matter were only just beginning to assemble out of the fire. By the time the universe was a few seconds old, something subtle had already happened. The most violent part of its childhood had passed. Not the heat, that was still staggering. Not the density, space was still packed with energy. But the universe had crossed a threshold. The basic particles of matter were now stable enough to persist. Protons existed. Neutrons existed. Electrons swarmed everywhere like sparks in a furnace. And photons, the particles of light, still dominated the entire environment. Yet for the first time, the raw ingredients of atoms were present at the same time. That may sound like a small step, but it was enormous, because until that moment, matter had been fragile. Every time particles collided, the energy was high enough to tear them apart again. But now the temperature had dropped below a critical point, still unimaginably hot, around 1 billion degrees Celsius, but finally low enough that protons and neutrons could begin to combine. The universe was entering its first true moment of chemistry, not the complex chemistry of molecules and reactions, just the earliest attempt at building atomic nuclei. The process began with something extremely simple: a proton and a neutron colliding. If the collision happened gently enough, which in that environment meant only moderately violent, they could stick together. The result was deuterium, a hydrogen nucleus containing 1 proton and 1 neutron. It is sometimes called heavy hydrogen. In today's universe, deuterium is rare. Only a tiny fraction of hydrogen atoms contain that extra neutron. But in the early universe, deuterium was the first crucial step toward building heavier nuclei. And for a while, it struggled to exist. Because even though the universe had cooled enough for protons and neutrons to bind together, it was still flooded with energetic photons. Photons carrying enough energy to smash newly formed nuclei apart. Imagine trying to build fragile glass sculptures in the middle of a hailstorm. Every structure you assemble shatters almost immediately. That was the deuterium problem. For the first few minutes after the Big Bang, every time a proton and neutron formed deuterium, a passing photon would break it apart again. The universe was still too hot, too bright, too violent for stable nuclei. So for a short time, protons and neutrons simply drifted through the plasma waiting for the universe to cool just a little more. This waiting did not last long, only a few minutes. But in cosmic history, those minutes were decisive. Because once the temperature dropped below roughly 1 billion degrees, the hailstorm weakened. Photons no longer carried enough energy to destroy every deuterium nucleus immediately. Some survived. And once deuterium could survive, nuclear reactions accelerated. Protons and neutrons began combining into helium nuclei. 2 protons, 2 neutrons, bound together by the strong nuclear force. Helium-4, the most stable light nucleus in the universe. The formation of helium happened rapidly. Within minutes, nearly every neutron available in the universe was locked into helium nuclei. Remember the earlier ratio, roughly 1 neutron for every 6 protons? Those neutrons could not remain free forever. They slowly decay when isolated. So when nuclear reactions finally began, the neutrons rushed into helium as quickly as physics allowed. The result was striking. About 25% of the universe's ordinary matter became helium. Not 25% by number, by mass. Because helium nuclei are heavier than hydrogen. That fraction has remained almost unchanged for 13.8 billion years. Stars would later produce more helium by fusing hydrogen in their cores. But the majority of helium in the cosmos was forged during these first few minutes, inside a universe still smaller, hotter, and younger than anything human intuition can easily grasp. Alongside helium, tiny traces of other elements appeared. Lithium formed in small amounts. A little beryllium, but the universe could not easily build heavier nuclei yet. The density dropped too quickly. Expansion pulled particles apart faster than nuclear reactions could continue. The nuclear furnace shut down. The entire era of primordial nucleosynthesis, the birth of the first nuclei, lasted only about 20 minutes. After that, the temperature fell too low for further fusion. The cosmic chemistry of the early universe froze into place. Roughly 75% hydrogen, roughly 25% helium, tiny traces of lithium, and almost nothing else. No carbon, no oxygen, no nitrogen, none of the elements that life eventually depends on. Those would come much later, inside the cores of stars, but already The early universe had established the basic ingredients of cosmic matter. And something remarkable happened when scientists calculated what those proportions should be. Long before we could observe the early universe directly, physicists predicted exactly these ratios. They calculated how protons and neutrons would behave in a cooling plasma, how nuclear reactions would unfold, how many neutrons would survive long enough to form helium. The answer consistently came out the same, about 25% helium. And when astronomers began measuring the composition of the oldest gas clouds in the universe, that prediction matched reality almost perfectly. Hydrogen and helium in exactly the proportions expected from a universe that began hot and dense. It was one of the earliest and strongest confirmations of the Big Bang. The early universe had left behind a chemical fingerprint. But even as the nuclear reactions faded, the cosmos was still far from calm. The temperature was still hundreds of millions of degrees. The plasma of electrons, nuclei, and photons remained tightly coupled. Light still could not travel freely. The universe was still opaque, yet something else had begun to shift. The expansion was slowly giving gravity an opportunity. Those tiny density fluctuations, the ones stretched across space during inflation, had survived all the violence. They were still there. Barely perceptible variations in density, one region slightly heavier, another slightly lighter. For now, radiation pressure kept everything mixed. But gravity was patient. Given time, even a difference of 1 part in 100,000 could grow. The denser regions would eventually pull in more matter. Gas would collect. Stars would ignite. Galaxies would appear. The large-scale structure of the cosmos was already encoded in those faint ripples, and every galaxy that would ever form was already quietly written into the early universe. Not as stars, not as clouds of gas, but as slight imbalances in a sea of radiation and plasma. The cosmic blueprint already existed, yet there was still a deeper mystery hidden inside those first minutes, because something had already happened earlier that made this entire process possible. Something small, almost invisible, yet decisive. During the violent particle storms of the early universe, matter and antimatter had been created constantly. Particle pairs emerging from pure energy, electrons and positrons, quarks and antiquarks, and every time matter met its mirror image, the result was annihilation. Both vanished, converted back into radiation. If the universe had produced equal amounts of matter and antimatter, that annihilation would have erased almost everything. The cosmos would have cooled into a thin sea of photons. No protons, no atoms, no galaxies, no observers. Yet the universe we see clearly contains matter. Stars, planets, people, which means that somewhere in the earliest moments the balance was broken. Not dramatically, not by a large margin, just slightly. For every billion antimatter particles created, there were about 1,000,000,001 matter particles. A tiny asymmetry. Almost nothing. But when annihilation swept through the early universe, destroying nearly all particle pairs, those extra survivors remained. Every proton in every star, every atom in every planet, every molecule in your body, all descended from that tiny excess. A 1 in a billion imbalance, written into the physics of the early universe. But where that imbalance came from remains one of the deepest unsolved questions in modern physics. Somewhere in the first second of cosmic time, the universe tipped slightly in favor of matter, and that small preference allowed everything else to exist. 3 minutes? That is roughly how long the universe needed to decide the basic chemistry of everything that would follow. 3 minutes after the beginning, the nuclear reactions of the early cosmos quietly shut down. Not because the ingredients were gone, but because the universe was expanding too quickly. Temperature had fallen, density had dropped. Protons and neutrons were now too far apart, moving too slowly to keep building heavier nuclei. The great cosmic forge cooled almost as soon as it began. What remained was simple. Hydrogen, helium, a trace of lithium. Almost nothing else. No carbon for life. No oxygen for breathing. No silicon for planets. The universe was chemically primitive, yet strangely balanced. About 75% hydrogen by mass. About 25% helium. That ratio would persist for billions of years, shaping the evolution of stars and galaxies long before the heavier elements appeared. And the most remarkable part is that this ratio was not chosen deliberately by the universe. It was set by a race between two processes, expansion and nuclear fusion. As the universe cooled through the billion-degree threshold, protons and neutrons suddenly found themselves able to bind together. But the clock was already running. Every second, space stretched. Particles moved farther apart. Collisions became rarer. The nuclear reactions had only a brief window in which they could occur. Inside that window, nearly every surviving neutron found a home inside helium nuclei. Because helium is extremely stable. Once formed, it is difficult to break apart. But hydrogen remained abundant. A single proton does not need a neutron to exist. So while neutrons rushed into helium, many protons remained alone. Those lone protons became the nuclei of hydrogen atoms. In a sense, hydrogen is simply the leftover fuel from the Big Bang, the element that did not have enough neutrons available to form anything heavier, and hydrogen would become the dominant building block of stars. Long before galaxies formed, the universe was already stocked with the raw material for stellar fire. Yet during those first minutes, another strange silence began to grow. The nuclear reactions faded. The temperature fell below a few 100 million degrees. The cosmic furnace dimmed. For the first time since the beginning, the universe stopped changing its chemical identity. The composition froze. Hydrogen and helium drifting through a bright plasma. Electrons still free. Photons still trapped. And the universe itself still only minutes old. If you could stand inside that moment, suspended in the early cosmos, it would not feel empty. It would feel dense. Heavy. Radiation pressing against everything. The density of matter would still be millions of times higher than the density of the air around you now. Every cubic meter of space packed with particles moving at near-light speeds. Yet compared to the earliest moments, this universe was already beginning to calm. The temperature continued falling. Minutes became hours. Hours became years. And with each passing moment, the density of the plasma dropped further. But light was still imprisoned. Photons could not escape the charged particles filling space. They scattered endlessly, like sparks trapped in a blizzard. This meant the universe had no visible horizon. Even if you had perfect eyes capable of surviving the heat, you could not see far. Light travelled only short distances before bouncing again. The cosmos was a glowing fog, every direction equally bright, every direction equally opaque. And that fog would persist for a long time, longer than the age of human civilization, longer than the existence of modern humans. For nearly 380,000 years, the universe remained a plasma, a luminous ocean of particles and radiation moving together. During that time, something else was quietly growing stronger. Gravity. At first, radiation pressure overwhelmed everything. Photons carried enormous energy. They pushed matter around. They kept the plasma smooth. But the faint density fluctuations left behind by inflation had never disappeared. They were still there. Tiny imbalances. One region slightly denser, another slightly emptier. Those differences were incredibly small. 1 part in 100,000. But gravity does not forget. Given time, even the smallest advantage becomes decisive. In denser regions, gravity began tugging matter inward. Not dramatically. The plasma resisted collapse. Radiation pressure pushed outward. The two forces wrestled constantly. Matter tried to fall into denser regions. Radiation pushed it back out again. The result was something like sound waves moving through the cosmic plasma. Regions compressed, then expanded. Tiny oscillations rippled through the young universe. Today we call them baryon acoustic oscillations. But in that early era they were simply the universe breathing. Slowly, subtly, a cosmic heartbeat carried through the plasma. These oscillations left patterns in the density of matter, patterns that still exist in the distribution of galaxies billions of years later. If you map galaxies across enormous distances, you find faint ripples in their arrangement, echoes of those ancient sound waves. The early universe was leaving fossils everywhere. Fossils in light, fossils in matter, fossils in the chemical composition of space itself. All records of a time when the universe was still young and turbulent. But something else had already happened during those first minutes that shaped everything that followed. Matter had survived. Against extraordinary odds, in the earliest moments, matter and antimatter were produced together, particle pairs emerging constantly from energy. Yet when those pairs met, they destroyed each other, converted back into photons. For a time, the universe was a battlefield of annihilation. Particle meeting antiparticle. Flash of radiation. Both gone. If the numbers had been perfectly balanced, the annihilation would have continued until almost nothing remained. The universe would have cooled into a sea of radiation. No atoms, no stars, no planets, but there was a tiny excess. For roughly every billion antimatter particles, there were about 1,000,000,001 matter particles. That extra particle survived each annihilation. A survivor left behind after the mirror images destroyed one another. All the matter in the observable universe comes from those survivors. Every atom, every galaxy, every living cell. All of it descends from a 1 in a billion imbalance written into the earlier seconds of cosmic time. Physicists call this mystery baryogenesis, the origin of the matter-antimatter asymmetry, and despite decades of research, we still do not fully understand how it happened. Something in the early universe favoured matter slightly over antimatter. Perhaps subtle violations of symmetry in the laws of physics. Perhaps new particles or interactions we have not yet discovered. Whatever the cause, that small asymmetry changed the destiny of the cosmos. Without it, the universe would be silent, dark, featureless. Instead, it became a place where matter could persist, where structure could grow, where stars could ignite. Yet even now, minutes after the beginning, none of those structures existed. No stars, no galaxies, no planets. Just hydrogen and helium nuclei drifting through a hot plasma. Electrons still unattached. Photons still trapped. But the universe was expanding, cooling, waiting, and eventually it would cross another threshold. A temperature low enough for electrons to slow down, low enough for them to attach themselves permanently to nuclei. When that happened, atoms would finally exist. Light would break free from the plasma, and the universe would become transparent for the first time. The glow released in that moment still surrounds us today, a faint microwave whisper filling all of space. The oldest light we can see, a photograph of the universe when it was only a few 100,000 years old. But even that ancient light carries deeper information, because hidden inside its faint patterns are the fingerprints of events that happened far earlier. During the first seconds, during inflation, during the violent birth of matter itself, the afterglow of a universe that began not in darkness, but in overwhelming light. The early universe came dangerously close to disappearing, not fading slowly, not collapsing, but annihilating itself almost completely. Because in the beginning, nature did not favour matter. Physics treats matter and antimatter almost as equals. For nearly every particle that exists, electrons, quarks, protons, there exists a mirror version with opposite charge. An electron has a partner called a positron. A proton has an antiproton. Quarks have antiquarks. When matter meets antimatter, the result is immediate. They vanish, converted into pure energy, usually high-energy photons. Nothing remains of the original particles, and the early universe produced these pairs constantly. Energy was so abundant that collisions between photons created particles and antiparticles everywhere. Quarks and antiquarks bursting into existence. Electrons and positrons appearing and disappearing in flashes of radiation. It was a universe where matter was not stable yet. It was temporary. Imagine standing in a room where sparks appear in the air around you every fraction of a second. Each spark immediately meets its mirror spark. They collide. Both vanish in a brief flash. That was the early universe. Particle, antiparticle, collision, light, over and over again. The strange part is that the laws of physics we know suggest this process should produce equal numbers of matter and antimatter. Perfect symmetry. For every electron, a positron. For every quark, an antiquark. If that symmetry had held perfectly, the next stage of cosmic history would have been very short. As the universe cooled, particles and antiparticles would eventually collide and annihilate faster than new pairs could form. One by one, they would disappear, protons with antiprotons, electrons with positrons, matter with antimatter, until nothing remained. Except radiation, the universe would become a thin bath of photons drifting through expanding space. No atoms, no stars, no galaxies, no chemistry, no observers, just light spreading into darkness. Yet that is not the universe we see. Look at the night sky. Every star is made of matter. Every galaxy contains billions of tons of it. Your body, every atom of it, is matter. Antimatter is rare. It appears in high-energy events, inside particle accelerators, in certain radioactive decays, in cosmic rays striking the atmosphere, but it does not fill the cosmos. The universe chose matter, or something allowed matter to win. The imbalance was unbelievably small. For roughly every billion antimatter particles produced in the early universe, there were about 1,000,000,001 matter particles. One extra. That is all. But the consequences were enormous, because when annihilation swept through the early cosmos, those extra particles survived. Imagine a room filled with 1,000,000,000 blue marbles and 1,000,000,000 red marbles. Each blue marble destroys a red marble when they touch. They disappear in pairs. When the collisions end, what remains? Just the extra marbles. If there were 1,000,000,001 blue marbles, then after annihilation there would be exactly one marble left. Everything else would be gone. The matter filling our universe is the cosmic equivalent of that leftover marble. The survivors of a massive annihilation event that erased almost everything. All the galaxies we see, all the stars, all the planets, all the atoms in your body, they exist because the early universe produced just slightly more matter than antimatter. But where did that imbalance come from? That question sits at the center of one of the deepest unsolved problems in modern physics. The laws governing particles are built on symmetries. Certain transformations, flipping charge, reversing direction, swapping particles for antiparticles, should leave the underlying physics unchanged. But experiments show that some of these symmetries are not perfect. In the 1960s, physicists discovered that certain subatomic particles known as kaons behave slightly differently from their antiparticles. Later, similar asymmetries were observed in particles called B-mesons. These phenomena are known as CP violation, charge parity symmetry breaking. It means the laws of physics treat matter and antimatter almost the same. But not quite. The difference is tiny. So tiny that the CP violation we currently observe in laboratory experiments is not strong enough to explain the enormous dominance of matter in the universe. Something else must have happened. Some process in the early universe tipped the balance. Perhaps new particles existed at extremely high energies. Particles that decayed in ways that slightly favored matter over antimatter. Perhaps subtle violations of symmetry occurred during the violent phase transitions of the early cosmos. Some theories suggest the electroweak transition, the moment when the electromagnetic and weak forces separated, might have created conditions where matter gained a slight advantage. Other ideas involve heavy neutrinos decaying asymmetrically in the early universe. The details remain uncertain, but we know one thing with remarkable confidence. The imbalance must have occurred very early, within the first fractions of a second, long before atoms existed, long before nuclei formed, long before galaxies began gathering. Somewhere in that violent youth of the cosmos, the laws of physics leaned, just slightly, toward matter, and the rest of cosmic history unfolded from that tiny preference. It is difficult to grasp how small the imbalance truly was. Imagine 1,000,000,000 raindrops falling. Now imagine one extra drop. That is the margin by which matter won. Yet that one drop became every planet, every star, every living thing, every human thought that has ever occurred. The universe is made of leftovers, remnants that survived a massive wave of annihilation early in time. And the annihilation itself was not quiet. When particles and antiparticles destroyed each other, they released energy, enormous bursts of radiation. The early universe flooded with photons produced by those collisions. That radiation still exists today, stretched and cooled by cosmic expansion. Those photons became part of the sea of light that filled the early universe. Light that would eventually escape hundreds of thousands of years later. Light that we still detect as the cosmic microwave background. But even after the annihilation era passed, the universe remained young. Only minutes old, still incredibly hot. Still filled with plasma, hydrogen and helium nuclei drifting through a storm of photons and electrons. Yet gravity was already waiting patiently. The tiny density fluctuations left by inflation still lingered. Barely noticeable differences in mass scattered through the plasma. At first, radiation pressure kept everything mixed. Matter could not collapse into structures yet. But time was on gravity's side. The universe continued expanding, cooling, spreading out, and slowly, the grip of radiation would weaken. When that happened, those faint ripples would grow. Gas would begin falling into denser regions. Clouds would form. Stars would ignite. Galaxies would take shape. The large-scale structure of the cosmos, the vast web of clusters and voids stretching across billions of light-years, would begin assembling, all because of tiny fluctuations, all because matter survived, and all because somewhere inside the first second of time, the universe chose not to be perfectly symmetrical. It chose imbalance. It chose survival. And that smallest symmetry allowed complexity to exist at all. But even now, in this early chapter of cosmic history, the universe remained opaque. Light still could not travel freely. The plasma still trapped photons in an endless scattering dance. The cosmos was glowing everywhere, yet no clear horizon existed. It would take hundreds of thousands of years before that fog would finally clear, before the first true light could travel unhindered across space, before the universe would reveal its earliest photograph, a faint glow that still surrounds us today, the oldest light we can see, a relic from a moment when the universe finally became transparent. But hidden inside that glow is something even older. Subtle patterns, tiny temperature differences, fossils of events that happened far earlier. Inside the first second, inside the violent birth of space, matter, and time. For hundreds of thousands of years, the universe remained a fog of light. Not darkness, not emptiness. A glowing, opaque ocean where radiation and matter were tangled together so tightly that neither could move independently. Photons, the particles of light, ricocheted constantly between charged particles. Electrons scattered them. Protons deflected them. Every direction filled with collisions. If you had been there, suspended inside that young cosmos, the universe would not look like space. It would feel like standing inside a dense, luminous storm. Light everywhere, yet no clear distance, because photons could not travel far before striking something. The entire universe behaved like a single, enormous plasma, and this state lasted for a surprisingly long time, 380,000 years. Longer than the entire span of recorded human history. Longer than the time between the building of the first pyramids and today, multiplied dozens of times. For all that time, the universe remained trapped in its own brightness. Yet slowly, almost imperceptibly, the environment was changing. Expansion continued. Space stretched. Density dropped. Temperature fell. From billions of degrees to millions, then to thousands. At first the change seemed minor, but eventually the universe approached a critical threshold, about 3,000 degrees Celsius. Still hot enough to melt steel, still hotter than lava, yet in cosmic terms this was a cool evening. Because at roughly that temperature, electrons finally slowed down enough to attach themselves to atomic nuclei. For the first time in cosmic history, atoms could exist. Before this moment, electrons were too energetic. They flew past nuclei at tremendous speeds. Any attempt to bind together was immediately broken by a passing photon. But as the universe cooled, electrons lost energy. Their motion slowed, and suddenly, when an electron passed near a proton, it could stay. Hydrogen atoms formed. Helium atoms formed. The charged plasma that had dominated the universe for hundreds of thousands of years quietly disappeared. Physicists call this event recombination. The word is slightly misleading. Electrons had never previously combined with nuclei in the early universe. But the name remained, and with recombination came something extraordinary. Transparency. Once electrons bound to nuclei, most photons no longer had charged particles to scatter from. The endless collisions stopped. Light could finally travel freely across space. Imagine a dense fog suddenly clearing. One moment visibility is only a few steps. The next moment the horizon appears. That was the transformation the universe experienced. In a relatively short span of time, the cosmos changed from opaque to transparent. Photons that had been trapped for hundreds of thousands of years were suddenly released. They began streaming through space, unhindered. Those photons are still travelling today. But the universe has expanded enormously since that moment. Every wavelength of light has stretched along with space. What began as visible and infrared radiation has cooled into microwaves. Today, those ancient photons fill the universe as the cosmic microwave background. A faint radiation field with a temperature of about 2.7 degrees above absolute zero. Every cubic centimetre of space around you contains hundreds of them. They pass through your body constantly. Invisible. Silent. Relics of the moment when the universe first became transparent. The discovery of this radiation in the 1960s changed cosmology forever. Because it was not random noise. It carried structure. Tiny variations in temperature scattered across the sky. Differences of only 1 part in 100,000. Almost perfectly uniform. Yet not perfectly smooth. And those tiny variations contained astonishing information. They were the imprints of the density fluctuations seeded during inflation. The same ripples we encountered earlier. Quantum fluctuations stretched across cosmic scales. Frozen into the radiation when the universe was only 380,000 years old. Each warmer spot in the microwave background corresponds to a slightly denser region of the early universe. Each cooler spot marks a region slightly emptier. The differences are incredibly small. A few millionths of a degree, yet those tiny variations would eventually grow under the influence of gravity. The slightly denser regions would pull in more matter. Gas would collect. Stars would ignite. Galaxies would form. The entire large-scale structure of the universe, the cosmic web stretching across billions of light-years, can be traced back to those faint temperature differences. The cosmic microwave background is essentially a photograph. The oldest light we can see, a snapshot of the universe when it was still a baby. But this photograph carries even deeper meaning, because the patterns within it allow scientists to reconstruct conditions that existed far earlier, long before atoms formed, long before nuclei, all the way back toward the first seconds after the beginning. When satellites like COBE first mapped the microwave background in the early 1990s, the variations they detected were astonishingly small. Later missions, WMAP and the European Space Agency's Planck satellite, measured them with exquisite precision. They revealed patterns consistent with sound waves rippling through the early plasma, those baryon acoustic oscillations we encountered earlier, compression and rarefaction moving through the cosmic fluid, frozen into the radiation when recombination occurred. These measurements told us something profound. The early universe was almost perfectly smooth. Almost. But not quite. Without those slight imperfections, gravity would have had nothing to work with. Matter would remain evenly spread. No stars, no galaxies, no planets, no observers. The universe would be a vast, thin fog of hydrogen and helium. Dark, featureless. Instead, the universe began with tiny ripples. Barely detectable, yet enough. Enough to grow. Enough to shape the cosmic landscape. The cosmic microwave background also revealed something else. The geometry of the universe. When scientists analyzed the size of those ancient sound wave patterns in the radiation, they discovered something surprising. The universe appears almost perfectly flat. Not curved like the surface of a sphere, not curved inward like a saddle, but flat. In geometric terms, that result fits remarkably well with the predictions of inflation. The violent expansion in the earliest moments would have stretched any curvature nearly smooth. Just as the surface of a balloon appears flatter as it expands, the microwave background became a kind of cosmic fossil, a relic that preserved information from the first moments of time. Every pixel in those sky maps is a message from the past, a photon that has travelled for nearly 13.8 billion years, crossing the expanding universe without interruption, until it reached our detectors, until it struck a radio antenna on Earth, or a satellite orbiting quietly above the atmosphere. The signal is faint, but unmistakable, a whisper from the infant universe. Yet the microwave background does not show us the beginning itself. It shows us the moment when the fog cleared, when light was finally allowed to travel freely. Earlier times remain hidden behind that glowing wall. like trying to look through the surface of the sun. Photons cannot carry information from before that barrier. To understand earlier moments, scientists rely on other clues: particle physics, the distribution of galaxies, the behavior of cosmic expansion, mathematical models grounded in observation, all of them pointing backward toward a universe that began hot, dense, and rapidly expanding, toward the first seconds, toward the violent transformations that shape the laws of nature, and perhaps even further, because the cosmic microwave background is not the final boundary. It is simply the oldest light we can see. Beyond it lies a deeper past, hidden not by darkness, but by brilliance. The blazing plasma of the early universe that once filled every corner of space. A time when the cosmos was still forming its basic structure, when the first atoms had not yet appeared, when the seeds of galaxies were only faint ripples in density, and when the consequences of the first second were still unfolding, because the universe we inhabit today, filled with stars and planets and vast empty space, is the cooled aftermath of that beginning. The quiet echo of a moment when reality itself was still deciding what it would become. Long before we built telescopes capable of seeing galaxies billions of light years away, the first clues about the beginning of the universe arrived as a quiet noise. Not a flash, not a dramatic discovery, just a faint hiss. It was the mid-1960s, and two radio engineers at Bell Laboratories, Arno Penzias and Robert Wilson, were testing a large microwave antenna in New Jersey. The instrument was designed to detect weak radio signals bouncing off satellites. Instead, it detected something else. A persistent background noise. A steady microwave signal that appeared no matter where the antenna pointed. Toward the center of the Milky Way. Toward empty regions of sky. Toward the horizon. Even straight upward into what should have been silent space. The signal was weak, but it refused to disappear. The engineers assumed the problem had to be technical. Perhaps interference from nearby cities. Perhaps noise inside the electronics. Perhaps something wrong with the antenna itself. They checked everything. They recalibrated instruments. They examined cables and receivers. They even climbed inside the giant horn antenna to clean out nesting pigeons and remove what they politely described in their notes as white dielectric material. The noise remained. A uniform microwave glow coming from every direction in the sky, at almost exactly the same temperature, about 3 degrees above absolute zero. Cold, incredibly faint. But everywhere, at nearly the same time, a group of physicists at Princeton University, led by Robert Dick, had been preparing an experiment to search for precisely such a signal. They were looking for the leftover radiation from the early universe, the afterglow of the hot Big Bang. When Penzias and Wilson contacted them to discuss the strange noise, the reaction was immediate. Dickey reportedly turned to his colleagues and said quietly, "Well, boys, we've been scooped." The engineers had accidentally discovered the oldest light in the universe. Radiation that had been travelling through space for nearly 14 billion years. A fossil from the moment when the universe first became transparent. What Penzias and Wilson detected was the cosmic microwave background. The faint glow left over from the time when electrons first combined with nuclei to form atoms. When photons were finally able to escape the cosmic plasma. When light was released to travel freely across space. Before that moment, the universe had been opaque. A dense fog of charged particles scattering photons endlessly. But once atoms formed, the fog cleared. Light streamed outward, and that light has been travelling ever since, across expanding space, across billions of years, until it reached Earth. Today we measure that ancient radiation with astonishing precision, but its existence alone told scientists something extraordinary. It confirmed that the universe once existed in a hot, dense state, a universe filled with radiation, exactly what the Big Bang model predicted. But the real story of the microwave background did not end with its discovery, because hidden inside that faint glow are patterns, subtle variations, tiny fluctuations in temperature across the sky, differences so small they are almost unimaginable, about 1 part in 100,000. If the average temperature of the microwave background is about 2.725 degrees above absolute zero, the variations are only a few millionths of a degree, a few microkelvin. Detecting them required decades of technological progress. In 1989, NASA launched a satellite called COBE, the Cosmic Background Explorer. COBE carried instruments sensitive enough to measure tiny variations in the background radiation. When its data arrived, scientists saw something remarkable. The microwave background was not perfectly uniform. It contained faint mottled patterns across the sky. Tiny hotspots. Tiny cold spots. These variations were exactly what cosmologists expected if the early universe contained slight differences in density. Regions slightly heavier, regions slightly lighter. COBE's map looked almost like static on an old television screen. But that static was the earliest structure in the universe. The seeds from which galaxies would eventually grow. Later missions refined the picture. The Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001. Then the European Space Agency's Planck satellite in 2009. These instruments mapped the cosmic microwave background with extraordinary precision. They measured not just the temperature variations, but their exact statistical patterns. And those patterns told a detailed story. They revealed how matter and radiation oscillated in the early plasma, the sound waves moving through the cosmic fluid. They measured the density of ordinary matter, the density of dark matter, the geometry of space itself, even the age of the universe. From those maps alone, scientists could calculate that the universe is about 13.8 billion years old. They could determine how much matter exists, how much dark energy drives cosmic expansion, and how the earliest fluctuations grew into the structures we see today. It is an extraordinary idea. By measuring tiny temperature differences in ancient light, we can reconstruct conditions that existed billions of years ago. Before stars, before galaxies, before atoms even existed. The microwave background acts like a photograph. But it is more than a photograph. It is also a record of motion. Those faint ripples represent sound waves moving through the early universe. Pressure pushing outward, gravity pulling inward. The plasma compressing and expanding rhythmically. Each oscillation left a mark in the radiation, frozen in place when atoms formed and light finally escaped. Even today, those ancient patterns still influence the distribution of galaxies across the cosmos. If you measure distances between galaxies across enormous scales, you find a preferred spacing, a faint echo of those early sound waves, a fossil imprint stretching across billions of light years. But the microwave background reveals something even deeper. The fluctuations within it follow a pattern predicted by inflation. The theory that the universe experienced an explosive expansion in its earliest moments. Inflation would have stretched tiny quantum fluctuations to cosmic scales. Exactly the kind of fluctuations we see in the microwave background. Random, but statistically precise. Not arbitrary noise. Structured randomness. The fingerprints of quantum physics written across the entire sky. That means the largest structures in the universe, galaxies separated by hundreds of millions of light years, may ultimately trace their origins to fluctuations smaller than an atom. Ripples in quantum fields stretched across space during the first fraction of a second. The cosmic microwave background does not show us inflation directly, but it preserves its consequences, evidence written into the oldest light we can observe. And that light has travelled an extraordinary journey. For nearly 13.8 billion years it has moved through expanding space, across regions that would eventually form galaxies, past stars that had not yet ignited, through clusters of matter that did not yet exist, until eventually it arrived here, a photon drifting quietly through the cosmos, then striking a detector on Earth, a whisper from the earliest chapter of time. But even this ancient light has limits. It can show us only as far back as the moment when the universe became transparent, about 380,000 years after the beginning. Earlier events remain hidden behind that glowing barrier. To reach further back, toward the first seconds, scientists must rely on other clues. Particle physics experiments, the behavior of cosmic expansion, the distribution of galaxies across vast distances, and theoretical models that connect the smallest scales of quantum physics with the largest scales of cosmology, all of them pointing toward a universe that began hot, dense, rapidly expanding, a universe where the laws of physics themselves emerge from a deeper symmetry, a universe shaped by events that unfolded inside the first second. Yet the deeper we look into that beginning, the more we encounter a boundary, a place where our understanding begins to fade, Because when we approach the earliest instant of all, the moment when time itself began, our current theories begin to lose their power. And beyond that boundary lies one of the greatest mysteries in science. What happened before the first moment we can describe? The cosmic microwave background looks quiet, a pale glow filling the entire sky, almost perfectly smooth. If you tune a sensitive microwave receiver and point it anywhere in space, you will measure the same faint temperature about 2.725 degrees above absolute zero. Cold, ancient, nearly uniform. At first glance, it feels almost empty of information. But hidden inside that smoothness is one of the richest datasets in all of science. Because those tiny temperature variations, the ones measured in millionths of a degree, form a pattern. And patterns can be read. Imagine looking down at the surface of a calm lake. At first it appears flat, but if you look carefully you see ripples moving across the water. Those ripples carry information about what disturbed the surface. A dropped pebble, a gust of wind, a passing boat. The early universe left similar ripples in the cosmic microwave background. But instead of water waves, these were pressure waves moving through a plasma of particles and radiation. The universe, when it was only a few 100,000 years old, behaved like a vibrating fluid. Gravity pulled matter inward towards slightly denser regions. Radiation pressure pushed outward. The two forces competed. Compression followed by expansion. Expansion followed by compression. Over and over. These oscillations moved through the early plasma like sound waves. Not sound you could hear, but the same physical principle. A wave travelling through a medium. In this case, the medium was the entire universe. The speed of those waves depended on the density and temperature of the plasma, and their size depended on how long they had been travelling before the universe became transparent. When recombination occurred, when atoms formed and photons escaped, the motion froze. The sound waves stopped, but their imprint remained. Regions that were compressed appeared slightly warmer in the microwave background. Regions that were expanding appeared slightly cooler. The result was a pattern of fluctuations across the sky. At first they look random, but when scientists analyze them carefully, something extraordinary appears. The fluctuations follow a precise statistical structure, a set of peaks and troughs in the distribution of sizes. These peaks correspond exactly to the wavelengths of those ancient sound waves. The largest waves had time to compress once before recombination. Slightly smaller waves completed a full cycle, compression and expansion. Even smaller waves oscillated multiple times. Each of these patterns left a distinct signature in the microwave background. By measuring the strength of these peaks, scientists can determine the physical conditions of the early universe. How dense the plasma was, how much ordinary matter existed, how much dark matter contributed gravitational pull, even how curved space itself might be. The analysis is almost like reading the resonance pattern inside a musical instrument. Strike a violin string and it vibrates at specific frequencies. From those vibrations you can infer the tension of the string, its length, and the material it is made from. The universe produced its own resonance pattern, and the microwave background preserves it. From that pattern we have learned something astonishing. Ordinary matter, the atoms that make up stars, our planets, and people, accounts for only a small fraction of the universe. About 5% of the total cosmic energy density. Another portion, roughly 27%, is dark matter. Invisible. Not made of atoms, detected only through its gravitational influence. And the remaining 68% appears to be something even stranger. Dark energy. A mysterious form of energy embedded in space itself, driving the accelerated expansion of the universe. These proportions are encoded in the microwave background, written into the tiny fluctuations that fill the infant cosmos. But the microwave background reveals more than composition. It also tells us about the geometry of space. When scientists measure the apparent size of those ancient sound waves across the sky, they find something remarkable. The universe appears extremely close to flat, not curved like the surface of a sphere, not curved like a saddle. Flat, at least on the larger scales we can measure. This result fits beautifully with the theory of inflation. If the universe expanded exponentially in its earliest moments, any initial curvature would have been stretched almost perfectly smooth. Much like the surface of a balloon appears flatter as it grows larger. Inflation predicted this. and the microwave background confirmed it. But perhaps the most profound information hidden in the microwave background lies in the distribution of those tiny fluctuations themselves. Their randomness follows a specific pattern predicted by quantum mechanics. During inflation, quantum fluctuations, microscopic jitter in energy fields, were stretched outward by the rapid expansion of space. Those tiny fluctuations became the seeds of cosmic structure. When we analyze the statistical pattern of temperature variations across the sky, we see exactly the kind of spectrum expected from quantum fluctuations stretched during inflation. It is an extraordinary connection. The largest structures in the universe, galaxy clusters spanning hundreds of millions of light years, may ultimately trace their origins to quantum events that occurred on subatomic scales. The universe took microscopic uncertainty and amplified it into cosmic architecture. Even now, billions of years later, the pattern is still visible. Galaxies cluster along filaments. Vast voids open between them. A cosmic web stretching across unimaginable distances. All of it evolving from those early ripples. All of it encoded in the faint patterns of the microwave background. Yet the microwave background also marks a limit. It is the oldest light we can see. Before that moment, before recombination, the universe was opaque. Photons could not travel freely. The plasma scattered them endlessly. Light cannot carry information from earlier times. It is like trying to see through the glowing surface of a star. The light we observe comes from the outer layer. The deeper interior remains hidden. So if we want to understand what happened earlier, the formation of nuclei, the birth of protons and neutrons, the separation of forces, the era of inflation, we must rely on other kinds of evidence. Particle accelerators recreate small glimpses of early universe conditions. The distribution of galaxies reveals the growth of those primordial fluctuations. Gravitational waves may one day provide direct clues about inflation itself. Each method offers a fragment of the story, but none can yet take us all the way back. Because as we approach the very beginning, the first fraction of a second, our theories begin to collide with a deeper mystery. Gravity and quantum physics, two of the most successful frameworks in science. Yet they refuse to fully agree when conditions become extreme. General relativity describes gravity and the large-scale structure of space-time. Quantum mechanics governs particles and fields at microscopic scales. Both work beautifully within their domains. But in the earliest instant of the universe, does both must operate at once. And that is where our understanding begins to break. The equations stop giving reliable answers. Space and time themselves may behave differently. Perhaps discretely. Perhaps fluctuating violently. We do not yet know. The microwave background tells us what the universe looked like 380,000 years after the beginning. Other evidence takes us back to minutes, then seconds, then fractions of seconds. But beyond a certain point, the trail fades. The earliest instant, the true beginning of time, remains hidden behind a boundary our current physics cannot yet cross. And that boundary marks one of the greatest unanswered questions in science. Not simply how the universe evolved, but what it means for a universe to begin at all. The deeper we push toward the beginning of time, the stranger the universe becomes. For most of cosmic history, our equations work beautifully. General relativity explains how gravity bends space. Quantum mechanics describes how particles behave at the smallest scales. Each theory has passed every experimental test we have thrown at it. Together they explain stars, black holes, atoms, chemistry, radiation, and the expansion of the universe itself. But when we try to follow the story all the way back toward the first fraction of a second, the two frameworks begin to clash. The early universe demands that both be true at the same time. Gravity was enormous. Density was extreme. Energy was concentrated into a tiny volume. Under those conditions, space-time itself becomes part of the quantum world. And that is where the mathematics stops cooperating. General relativity treats space-time as smooth, a continuous fabric that bends under the influence of mass and energy. Quantum mechanics, by contrast, allows uncertainty everywhere. Fields fluctuate. Particles appear and disappear. Nothing remains perfectly still. When those two descriptions meet at extreme energies, the equations explode with infinities. Predictions stop making sense. Our models begin to break down. Physicists sometimes refer to this boundary as the Planck era. a moment earlier than about 10 to the power of minus 43 seconds after the beginning. The Planck time. Before that moment, our current theories cannot reliably describe what happened. It is not simply that we lack measurements. It is that the mathematics itself stops behaving. To understand why, consider the scale involved. The Planck length, roughly 1.6 times 10 to the power of minus 35 meters, is unimaginably small. If an atom were expanded to the size of the observable universe, the Planck length would still be smaller than a grain of sand. At that scale, quantum fluctuations of spacetime itself become enormous. Space may no longer behave like a smooth surface. It may resemble something more chaotic, something like foam. Tiny regions of spacetime bubbling, collapsing, and reforming continuously. Distances fluctuating. Time itself uncertain. Physicist John Wheeler once described this hypothetical structure as quantum foam, a universe where geometry itself is unstable, where the concept of a smooth spacetime path might not even exist. In that environment, asking where something is becomes difficult. Even asking when something happens may lose clear meaning. Time and space, the stage on which physics normally unfold, may themselves become dynamic, fluctuating objects. And that raises a deeper question. If time behaves differently at those scales, what does it mean to ask what happened before the beginning? The Big Bang is often described as the start of everything. But the phrase can be misleading. The Big Bang was not necessarily an explosion occurring at a specific point inside space. It was the moment when space itself began expanding from an extremely hot and dense state. The equations of general relativity describe this expansion well. But if we run them backward far enough, something strange appears. Density rises, temperature climbs, curvature increases. Eventually everything approaches an infinite value, a singularity, a point where the equations predict infinite density and zero volume. But physicists rarely interpret this singularity as a literal object. Instead, it signals a breakdown in the theory, a place where the mathematical description stops being reliable. Much like dividing by zero in ordinary arithmetic, the infinity is not necessarily real. It is a warning that the model has reached its limit. So the true beginning of the universe may not have been a singularity. Something else could have happened before the earliest moment we can currently describe. Many ideas have been proposed. Some suggest that the universe emerged from a quantum fluctuation in a vacuum. In quantum mechanics, empty space is never perfectly empty. Energy fluctuations occur constantly. Particles briefly appear and vanish. Some cosmologists have speculated that a sufficiently large fluctuation could produce an entire expanding universe. Others explore the possibility that the Big Bang was not the beginning at all. Instead, it may have been a transition, a bounce. In certain models, the universe existed in a previous contracting phase. Matter collapsed inward. Density increased. But instead of reaching a singularity, quantum effects halted the collapse and triggered a new expansion. The Big Bang would then represent a rebound rather than an origin. Some theories go further still. In certain versions of inflation, the rapid expansion of space may occur repeatedly in different regions of a larger cosmic environment. New universes budding off like bubbles, each with its own physical conditions, each expanding independently. If such a process exists, our universe could be one region among many, a tiny pocket within a vast multiverse. These ideas remain speculative. They are mathematically intriguing but difficult to test directly. And science demands more than possibility. It demands evidence. Yet even without knowing what happened before the earliest moment we can describe, the evidence for the early hot universe itself is overwhelming. The cosmic microwave background, the abundance of hydrogen and helium, the expansion of galaxies, the growth of cosmic structure, all of it points backward toward a universe that began hot, dense, and rapidly expanding. But the closer we approach the first instant, the more the familiar concepts begin to dissolve. Distance loses meaning. Time becomes uncertain. Energy and geometry intertwine. The boundary between existence and description becomes thin. It is an unusual situation in science. We understand enormous portions of cosmic history in extraordinary detail. We can model the formation of galaxies billions of years after the beginning. We can measure the conditions minutes after the Big Bang. We can calculate nuclear reactions in the first few seconds. But the earliest instant itself remains hidden behind a veil of incomplete physics. And yet something about that mystery feels almost fitting. Because the beginning of the universe was not simply the start of matter or light. It was the start of space, the start of time, the start of the physical stage on which every later event would unfold. Even our language struggles to capture that idea. We are used to asking what happened before something. Before sunrise, before the earth formed, before stars ignited. But if time itself began with the expansion of the universe, then the question before may not apply in the usual sense. It may be like asking what lies north of the North Pole. The direction itself stops existing beyond a certain point. Whether that interpretation is correct remains uncertain. Future discoveries may reveal deeper layers of reality, a quantum theory of gravity, new particles, new symmetries, new evidence written into the structure of space-time itself. But for now, the earliest moment remains a frontier, a place where the known laws of physics fade into questions. Yet the universe we inhabit today still carries the consequences of whatever happened there. The shape of cosmic expansion, the patterns in the microwave background, the existence of matter itself, all of it echoes that first moment, a moment when the universe began its long transformation from a hot, dense origin into the vast cosmic landscape we see today. And even though the first instant may still hide beyond our understanding, the rest of the universe has spent 13.8 billion years revealing what came after. The expansion that began in the first moments of the universe never stopped. It did not slow to zero. It did not reverse. It is still happening now. At this very moment, the space between galaxies is stretching. Clusters of galaxies drift apart. Light traveling through the cosmos slowly lengthens its wavelength as the fabric of space expands beneath it. This expansion is not something we feel locally. Gravity holds galaxies together. It holds stars in their orbits. It binds planets to stars and atoms to themselves. But on the larger scales, or across tens of millions of light years and beyond, the expansion becomes unavoidable. The universe is growing, and it has been doing so since that first second. In 1929, the astronomer Edwin Hubble noticed something strange when he measured the light from distant galaxies. Their spectral lines, the fingerprints of chemical elements, were shifted toward the red end of the spectrum. Redshift. Light stretched to longer wavelengths. At first glance, it might look like the galaxies themselves were racing through space away from us. But the pattern was deeper. The farther a galaxy appeared, the faster it seemed to recede. Every direction showed the same behavior. Not just a few galaxies, all of them. The most natural explanation was not that galaxies were flying outward from a central point. Instead, space itself was expanding. Every galaxy riding along with the growth of the universe. The analogy often used is a loaf of rising bread. Imagine raisins embedded in dough. As the bread expands in the oven, every raisin moves away from every other raisin. No raisin sits at the center of the expansion. The dough itself stretches. That is what space is doing. The farther apart two galaxies are, the more space lies between them. And the more space expands over time, which means their separation grows faster. This relationship, distance proportional to recession speed, became known as Hubble's law, a simple equation describing the expansion of the universe. But it also contains a remarkable implication. If the universe is expanding today, then in the past it must have been smaller. Run the cosmic film backward. Galaxies move closer together. Distances shrink. Temperatures rise. Matter becomes denser. Follow that process far enough, and everything converges toward the hot, dense beginning we call the Big Bang. This insight transformed cosmology. The universe was not static. It had a history, a beginning, a long evolution stretching across billions of years. But the expansion did not remain constant. Gravity works against it. All matter in the universe pulls inward. Galaxies attract one another. Clusters tug on neighboring structures. For decades, astronomers expected gravity to gradually slow the expansion, perhaps even halt it someday. If enough matter existed, the universe might eventually collapse back inward. A cosmic reversal sometimes called the Big Crunch. But observations in the late 1990s revealed something unexpected. When astronomers studied extremely distant supernova explosions, stellar deaths bright enough to be seen across billions of light years, they found that the expansion of the universe was not slowing down. It was speeding up. Galaxies were drifting apart faster than expected. Something was pushing the cosmos outward. Not ordinary matter. Not gravity. Something embedded in space itself. This mysterious influence became known as dark energy. Today, dark energy appears to dominate the large-scale behavior of the universe. Roughly 68% of the total cosmic energy budget is attributed to it. Its exact nature remains unknown, but its effect is clear. The expansion of the universe is accelerating. Space is stretching faster with time. The seeds of that expansion were planted in the earliest moments. Inflation may have been the first episode, a brief and explosive growth that shaped the large-scale geometry of the cosmos. But the quieter expansion that followed has continued for billions of years, and it still carries the fingerprints of those earliest conditions. The distribution of galaxies, the faint ripples in the cosmic microwave background, the abundance of hydrogen and helium, even the large-scale cosmic web, filaments of matter stretching across hundreds of millions of light-years, all trace their origins back to fluctuations born in the first fraction of a second. When we observe distant galaxies, we're also looking backward in time. Light from a galaxy 10 billion light-years away left that galaxy 10 billion years ago. We see it as it was when the universe was young. Telescopes become time machines. The deeper we look, the closer we approach the beginning. The most distant galaxies currently known formed only a few 100 million years after the Big Bang. A short time in cosmic terms. Their light has been travelling ever since, crossing expanding space, carrying information from an era when the first stars were igniting. And even beyond those galaxies lies something older. The cosmic microwave background. The afterglow of the moment when atoms formed and light finally escaped the early plasma. Beyond that glow lies the earlier universe we cannot see directly. The first minutes, the first seconds, the era of nuclear formation, the era of inflation, the earliest transformations that set the stage for everything that followed. Yet even now, billions of years later, the consequences of those first seconds are still unfolding. Every star that forms from collapsing clouds of hydrogen traces its origin back to the primordial hydrogen produced in the Big Bang. Every heavy element forged inside stellar cores builds on that early foundation. The oxygen you breathe, the carbon in your cells, the iron in your blood, all of them began as hydrogen nuclei formed in the earliest moments of cosmic history. Inside stars, hydrogen fuses into helium, helium into heavier elements. Stars live. Stars die. Supernova explosions scatter those elements into space. New stars and planets form from that enriched material. Eventually, in at least one corner of one galaxy, chemistry becomes complex enough for life. All of that unfolds across billions of years. Yet the entire process began with the conditions set during the first second. The expansion rate, the tiny density fluctuations, the survival of matter over antimatter, the formation of hydrogen and helium, the geometry of space itself, each one determined during the earliest moments, each one necessary for the universe we see today. The first second was not just a beginning. It was a blueprint, a set of physical conditions written into the structure of reality. And every galaxy drifting through space today is still following that design. But there is one final perspective worth considering. Because the beginning of the universe is not just something that happened long ago. In a very real sense, it is still happening. Space continues to expand. The cosmos continues to evolve. The laws of physics that emerged during those first moments still govern everything we observe. The first second did not simply end. Its consequences have been unfolding for nearly 14 billion years. And the universe has never stopped carrying the memory of that beginning forward. Every atom around you carries a memory older than the Earth, older than the Sun, older than the Milky Way, long before our planet formed, long before the first star lit the darkness of the young universe. The basic ingredients of matter had already been written into existence. Hydrogen, helium, a trace of lithium, nothing else. Those simple nuclei drifted through space for hundreds of millions of years before the first stars appeared to transform them into heavier elements. Yet those early atoms were not born in stars. They were born in the fading heat of the Big Bang itself. And if you follow their history backward far enough, every atom in your body leads to the same place. The first second, a moment when the universe was smaller, hotter, and stranger than anything we can easily imagine. It is tempting to think of that moment as distant, ancient, a kind of cosmic preface to everything that came later. But the beginning of the universe is not just something buried in the past, it is woven into the present, because the expansion that began then has never stopped. The universe has never returned to stillness. Every second, the fabric of space stretches a little more. Galaxies drift farther apart. Light crossing the cosmos slowly loses energy as its wavelength stretches with the expanding universe. Even the ancient photons of the cosmic microwave background are still cooling as space grows larger. The universe today is the cooled echo of that first moment, the quiet aftermath of a beginning so violent that it reshaped the laws of physics themselves. Yet the universe did not simply explode into chaos and fade. Something remarkable happened. Order emerged. Tiny fluctuations in density, smaller than 1 part in 100,000, became the seeds of galaxies. Gravity gathered matter into stars. Stars forged heavier elements. Supernovae scattered those elements across space. Planets formed. Chemistry became complex. And in at least one small corner of the cosmos, atoms arranged themselves into structures capable of asking questions, capable of wondering how the universe began. The entire chain of events traces back to the conditions set during the first second. The rate of expansion, the balance of forces, the survival of matter over antimatter, the faint ripples stretched across space during inflation. None of these parameters had to be exactly what they are. A slightly faster expansion might have prevented matter from gathering into galaxies. A slightly stronger gravitational pull might have collapsed the universe too quickly. A perfectly symmetrical balance between matter and antimatter would have erased all structure entirely. The universe could have been very different. Cold and empty. Smooth and silent. Instead, it became a place filled with stars. With galaxies. With complexity. With observers capable of tracing the story backward. This does not necessarily mean the universe was designed for life. Physics does not make such claims. But it does reveal something curious. The conditions established during the earliest moments allowed complexity to grow, and once those conditions existed, the rest of cosmic history unfolded almost inevitably. Gravity gathered matter. Stars ignited. Heavy elements appeared. Planets formed. Given enough time, chemistry explored possibilities. Most of those possibilities remained sterile, but a few did not. The atoms inside you once travelled through stars. They were forged in nuclear furnaces that ignited billions of years after the Big Bang. Yet the hydrogen at the heart of those stars was older still. It came directly from the first minutes of cosmic time, and those protons themselves emerged from the cooling energy of the universe less than a second after it began. Your body contains particles that are nearly as old as the cosmos itself. Particles that survived the annihilation between matter and antimatter. Particles that drifted through the expanding universe long before the Milky Way existed. Particles that once moved through a hot plasma where light could not yet travel freely. In that sense, the beginning of the universe is not just a story about the past, it is a story about what everything still is. The atoms around us are relics of that origin. The cosmic microwave background still fills space with ancient light. The expansion of the universe continues to carry galaxies apart. Even the faint density fluctuations born in the earliest fraction of a second still shape the large-scale structure of the cosmos today. The universe has been evolving for 13.8 billion years. But it has never erased its beginning. It carries that first moment forward, encoded in its chemistry, written into its geometry, visible in the faint afterglow of ancient radiation. And perhaps the most remarkable part of the story is that the universe allows us to read it at all. Light has travelled across billions of light years carrying information from the distant past. Telescopes capture photons that began their journey before the Earth existed. Detectors measure temperature differences smaller than a millionth of a degree. Particle accelerators recreate conditions that existed in the first fractions of a second. Piece by piece, humanity has reconstructed the story of the cosmos, a narrative stretching from the first instant of time to the present moment. Yet the deeper we look, the more the story opens outward. Because the beginning still holds unanswered questions. What triggered inflation? Why did matter slightly outnumber antimatter? What happened during the Planck era? when quantum physics and gravity intertwined? Did the universe emerge from a deeper reality, or is it one region within something larger? Those questions remain open. The first second still hides secrets. But even without the final answers, something extraordinary is already clear. The vast universe we inhabit, the galaxies, the stars, the quiet darkness between them, did not arise from slow, gentle beginnings. It emerged from a moment of unimaginable intensity, a moment when energy filled every corner of space, when the laws of physics were still settling into the forms we recognize today, when the seeds of cosmic structure were written into the fabric of reality, and all of it unfolded inside a single second. A moment so small it would vanish in the blink of an eye, yet powerful enough to shape the entire history of the universe that followed. The night sky feels ancient when we look at it. Calm, stable, endless. But every star we see is part of a story that began in that first second. A story still unfolding, and every time we look upward into the darkness, we are looking at the long, quiet aftermath of the universe's first breath.